All right, guys, so take out your packets and I want you to go to page 55. And I want you to take a couple minutes and try to answer these questions on your own and then compare with your group and come up with some ideas. So pause the video and answer these 3 questions now. All right, once you've talked through these 3 questions with your group, we're going to go on to the next page and kind of talk through some ideas. So this page has the definition of forces. A force is an interaction between 2 different objects that results in a push or a pull, which makes it a vector, meaning that it has direction. A couple things to note: an object can exert a force on itself, and we measure forces in units of newtons. So like 12 newtons would be what a force would be. So I'm going to go through a couple of these examples, and I want you to sketch what I'm drawing with your in your packet. So the first force, and maybe you guys talked about this at your table, is friction. Maybe you didn't, but friction is a force, and all friction is slowing things down or resisting motion. It's always parallel to the surface the object's sliding on and opposite the direction you're sliding or intended to slide. So let's draw an example. So draw a surface, like the floor, and then let's draw a box. So boxes are very helpful for forces. And let's assume this box is sliding to the right. Okay, so I'm going to write sliding to the right. So make a note of that to yourself. If this box is sliding to the right, then which way would friction be? Well, friction would be working against that, and so we would have friction going this way, and we'd label it F sub F. And that's not the only force acting on it, right? If it's sliding to the right, there might be some other forces acting on it. Let's talk about tension, the next one down. Tension is a pull force, so tension is always pulling, and it's always along a string. So an example of tension would be, let's make a box that's hanging from the ceiling, okay? So this box is hanging from the ceiling. It's being pulled down, but what's keeping it up? How come it's not falling towards the ground? Well, that's because we have some tension acting on it. So I'm going to redraw it and label this force Ft. So we always draw the arrows away from the object, and they have to be arrows, right, to show us that it's a push or a pull. That's what a force is. All right, we also have the force of gravity. Hopefully you guys talked about that one at your groups. The force of gravity is an attractive force, so a pulling force, between 2 objects with mass. So for example, you and the Earth. On Earth, force of gravity is always pulling straight down. So if we go back to our examples up here, this box hanging from the ceiling would also have force of gravity pulling down, right? This box sliding around the ground has gravity pulling it down. Gravity is an easy one because we almost always have gravity, right? We'd have to go really, 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 really far away from the Earth to not have gravity. And so we got force of gravity in both of those. Normal force. Normal force you might have heard of if you've taken an engineering class, but normal force is the force on the object due to the surface. What does that mean? That means like if I climbed up on the table, how come I didn't fall through? It's not just because the table's in the way. The table's actually pushing back on me. And so that we call that force that the table exerts on me the normal force. Why is it normal? Normal means perpendicular, and so it's normal to the surface or perpendicular to the surface. So if we go up to our first example, we had that box sliding to the right. Here we would have a normal force pushing up on that box. Okay? And our last one that we're going to talk about is push or pull forces. We're going to call it FA, for A is for applied force. We use applied force for any pushes or pulls that don't fit into any of these categories above. So if this box up here was sliding to the right, maybe there was an applied force, someone's pushing it to the right. Okay, we could call that that. And then we have our, I wouldn't say we have an applied force on the middle one because that's tension and gravity. We've done gravity, normal, awesome. So one other force we're going to talk about, and this isn't really a different force, but is net force. Net force is the sum of all the forces acting on an object. And so we're going to talk about adding up all the forces. Is there more force to the right, more force to the left, more force up, more force down? Or if they're all equal, then the net force is 0. So we'll always separate net force horizontally in the x direction and vertically in the y direction. So what we kind of did up there are called force diagrams or free body diagrams. And so I'm going to go through the first one on page 57 with you. But we're going to go through these steps. This is how you will always draw a free body diagram for our class. So let's go to the next page and remind ourselves of the instructions. So it says first thing you should do, so you should be looking at 56 and 57 right now, says represent the object with a box. So here's my picture. A box is sitting motionless on the floor. I'm going to redraw that box here. Okay, this is where my free body diagram is going to go. Seems kind of silly right now because you just have a box, but they're going to get more and more complicated. So represent the object with a box. If it's touching a surface, draw in that surface. So a floor is considered a surface. So I'm going to represent the surface with a dotted line underneath. The reason I do that is going back to that normal force. Normal is perpendicular to the surface, so I'm drawing in my surface here. Then number 3, draw all forces starting from the box using vectors or arrows that are proportional to the size of the force. So now we think about what forces are acting on it. Well, we definitely have gravity, right? We're on Earth. Gravity is pulling down. And then since it's sitting on that surface and I drew that in, that means I have a normal force pushing up on the box. Okay, surfaces exert normal forces. Step number 4 on page 56 says indicate which forces have equal magnitudes using tick marks. This box is not moving, so these two forces have to be equal in size, right? Everything up has to be balanced by everything down. Now we're going to fill in this box over here the velocity and acceleration and the F net. So if it's motionless, what's the velocity? Well, it's 0. What's the acceleration? Well, it's not moving, so it has no acceleration. And then net force, since it's not moving, these two forces up and down are balanced, so there is no net force. That's pretty boring, but that's kind of, we're always going to go back to filling that one in. The last thing we're going to do is write net force equations. So net force equations, we'll write F net X and F net Y. So what that means, again, is that is the sum of all the forces acting in the x direction. So horizontally, we have no forces acting right or left. So this is just 0. Vertically, we have 2 forces acting. So we've got the normal force and we have the gravity. Now, in the net force equation, I like to show different directions. So normal force is up, so I'm going to make it positive. And then gravity is down, so I'm going to add a negative Fg on there. Now, the reason I made it negative is because it's going down. Now, we said here those are balanced, so if I added a normal force plus a negative Fg, I would get 0. So there's still no net force equation, which is good. This should match what I wrote up here. All right, pause the video and try number 2 with your group. All right, hopefully you have something like this, gravity pulling down, tension pulling up. There's no surface. A string's not a surface, and that ceiling isn't touching the box, so there's no surface in my diagram. No surface is touching the box. So I've got gravity pulling down, tension pulling up. It's still motionless, so still no velocity, no acceleration, and those forces are balanced, so there's no net force. The net force equations are going to be very similar to what we wrote before. The net force in the horizontal direction or the x direction, there's no forces right or left, so that's 0. F net y is going to be Ft plus a negative Fg is equal to 0. All right, pause me again and do the next one with your table. All right, so let's talk through this free body diagram. We still have gravity and normal force because I'm on a surface. So a lot of people forget the vertical ones when we start to add horizontal ones. I labeled the force to the right F applied. If you just called it F, that's okay. But why isn't the box moving? Well, there has to be a force acting against the applied force. And so that has to be this force here. This is friction. And so friction's acting against, and I made those equal, showing that we're not moving. So my velocity is 0, acceleration 0, net force is still 0. And if I write my net force equation, now I have forces in the x direction. So I'm going to say F applied plus a negative force of friction is 0. If you had those flipped, that's okay. It just has to be one plus a negative the other. So right and left have to have it. One has to be negative, one has to be positive. And then in the y direction, I have F net, or a normal, plus negative Fg, and that's equal to 0. All right, one more. Pause me and then check out the answer. All right, so if you thought it looked exactly the same as number 3, you would be correct. The only thing that changes in this one is it says that it pushes, okay, instead of pulling. So it's still to the right, it's still an applied force, friction's still keeping it in place, so I just copy and pasted in my picture. It's the exact same thing for those two. All right, hopefully that helps you with forces, and have a great day.